So hi everyone. In this class, let we see some theorems based on monotonic sequence. Okay, whether it is monotonically increasing sequence or monotonically decreasing sequence. Here, a theorem is there that is every monotonically increasing sequence which is bounded above converges to its least upper bound. Means we have to take a monotonically increasing sequence and that is which is bounded above and that converges to its least upper bound. So in the statement have given that monotonically increasing sequence which is bounded above. So we have to take monotonically increasing sequence which is bounded above and how to prove that it converges to its least upper bound. Okay, so proof for this is, so let A and be a monotonically increasing sequence. We use the definition of monotonically increasing sequence and which is bounded above. Let A and be a monotonically increasing sequence which is bounded above. So here what I take, let U be least upper bound of the sequence AN. And we shall show that AN converges to U. Because here we are taking as U is the least upper bound of the monotonically increasing sequence which is bounded above. Okay. So here using the definition I write let epsilon greater than 0 be given. Since U minus epsilon is less than U. Okay. U minus epsilon is less than U. So therefore U minus epsilon is not an upper bound of AN. Because it has to be U is greater than U plus epsilon. Okay, so then it is upper bound. Okay, no problem that. So but here we are U minus epsilon is not an upper bound of sequence AN. So there exists a positive integer m such that AM is greater than U minus epsilon. Since AN is monotonically increasing, therefore we can write AN is greater than equal to AM is greater than U minus epsilon. For all n greater than equal to m. So using this we can write AN is greater than U minus epsilon for all n greater than equal to m. So also U is the least upper bound of sequence AN because already we have taken that. So using that we can write UN is less than or equal to U plus epsilon. AN is less than or equal to U plus epsilon for all n belongs to n. So therefore AN is strictly less than U plus epsilon for all n belongs to n. So using equation 1 and 2 we can write here, so lower bound less than AN is less than upper bound. Okay. So therefore using this equation I can write modulus of AN minus U is less than epsilon for all n greater than equal to m. So that implies that limit n tends to infinity AN is equal to U. So therefore sequence AN converges to U. So what I did here, I have used the definition of monotonically increasing sequence which is bounded above and proved that it converges to its least upper bound. Okay. So this is the theorem. So this is the simple proof. Okay. So it follows by your definition. So in the similar manner another theorem is there that is every monotonically decreasing sequence which is bounded below converges to its greatest lower bound. So here we have to take the definition of monotonically decreasing sequence which is bounded below and we have to prove that it is converges to its greatest lower bound. So here I have written a simple proof that is let AN be a monotonically decreasing sequence which is bounded below. So here I am taking L be its greatest lower bound of the sequence. AN. So here we have to prove that sequence AN converges to L. So let epsilon greater than 0 be given. Okay, since L plus epsilon is greater than L. So this is not the lower bound. Okay, so therefore L plus epsilon is not a lower bound of the sequence AN. There exists a positive integer m such that AM is less than L plus epsilon. Since an is monotonically decreasing, so we write here an is less than or equal to am is less than L plus epsilon. Means an is less than L plus epsilon for all n greater than or equal to m. So I take it as equation number 1. And we know that L is the greatest lower bound of the sequence an. So already we have written above. So therefore I can write it here, an is greater than or equal to L is greater than or equal to L minus epsilon. L minus epsilon. Therefore n is greater than L minus epsilon for all n belongs to n. So using equation 1 and 2, here we have found both the bounds, lower bound as well as upper bound. So we can conclude here that L minus epsilon is less than an is less than L plus epsilon using equation 1 and 2. Okay. So therefore this can be written as modulus of an minus L is less than epsilon. So this implies that this can be rewritten as limit n tends to infinity an is equal to L. Therefore sequence an converges to L. Sequence an converges to L. So what we have did here, we have taken monotonically decreasing sequence which is bounded below and which converges to its greatest lower bound. Okay. So this is the proof of your second theorem. So next result let me discuss, that is another theorem that is every monotonically increasing sequence which is not bounded above diverges to infinity. Every monotonically increasing sequence which is not bounded above diverges to infinity. Let, here also I am taking monotonically increasing sequence which is not bounded above, whether it is diverges to infinity or not, we have to check it. So proof for this is, let an be a monotonically increasing sequence which is not bounded above. So what I am taking here, let an be a monotonically increasing sequence which is not bounded above. That is already given in the theorem statement. So then given any k greater than 0, however large, there exists a positive integer m such that am is greater than k. So here because bounded, this sequence is monotonically increasing sequence that is not bounded above. Okay, that is the statement. And whether it is diverges to infinity or not, we have to check. So here I am taking, given any k greater than 0, however large, there exists a positive integer m such that am is strictly greater than k. Since an is monotonically increasing, that is an is greater than or equal to am is greater than k, means an is greater than k for all n greater than or equal to m. Means here we are not getting the upper bound, exact upper bound, means this is not bounded above. So therefore we can write here, this implies that limit n tends to infinity an is equal to infinity. This implies that an diverges to infinity, because we know that a sequence diverges when if limit n tends to infinity an is equal to whether it is infinity or minus infinity. This is the definition of divergent sequence. Okay. So another theorem is, that is every monotonically decreasing sequence which is not bounded below diverges to minus infinity. So means which is not every monotonically decreasing sequence which is not bounded below diverges to minus infinity or not, we have to check it. So proof for this is, let n be a monotonically decreasing sequence. Which is not bounded below. Then given any k greater than 0, however large, there exists a positive integer m such that am is less than minus k. It is moving towards minus infinity, minus k. Okay. So since an is monotonically decreasing, therefore an is less than or equal to am is less than minus k for all n greater than or equal to m. So this implies that an is less than minus k. So using the definition, we can write it as limit n tends to infinity an is equal to minus infinity, because you are minus k reaching towards minus infinity. If you take kth value, then it is moving towards minus infinity. Therefore limit n tends to infinity an is equal to minus infinity. Therefore this implies that sequence an diverges to minus infinity. So here we have taken monotonically decreasing sequence which is bounded below and proved that diverges to minus infinity. minus infinity. Thank you. So if you have any doubts regarding these proofs, so you can ask any questions, or you put your questions in the comment box of YouTube channel. Thank you. Thank you, one and all.